All right, welcome to part 2 of our lectures on conservation laws. So continuing on, let's introduce a new conservation law, one for strangeness. Okay, let's understand, what do we mean by that? Well, since the early days of particle accelerators, a certain class of particles was discovered that had a very strange property. They could be produced copiously and quickly in hadron collisions via the strong nuclear force. But rather than decay quickly, like with lifetimes of order 10 to the minus 22 seconds, which is characteristic of the strong force, they lived for an anomalously long time, 10 to the minus 10 seconds, which is more in line with the weak force. Now, 10 to the minus 10 seconds is still a tenth of a nanosecond. It's pretty short on human scales, but it's a trillion times longer than the 10 to the minus 22 seconds for a particle that decays via the strong force. So that's eons, right? The other thing is, it was found that these particles were observed to be produced only in pairs. So, for example, a charged pion can collide with a proton to make a K plus and a sigma plus baryon. That conserves electric charge, by the way. But both of the K plus and the sigma plus were one of these strange particles. Or it could have been a K plus and sigma minus if it was a pi minus that collided with the proton. Or you could have made neutral versions. You could have pi minus colliding with a proton to make a K0 and sigma 0, or a K0 and a lambda 0. So they always came in pairs, these strange particles, these kaons and these sigmas and lambda baryons. But the examples of slow decays are shown here. The sigma plus, for example, could decay to a neutron in pi plus. Well, that's good. The sigma plus is a baryon, and we have to conserve baryon number, so there's a neutron on the right side. So baryon number is +1 on both sides. Electric charge is conserved +1 here, 0 and +1 there from the pion. Everything's good, just was slow in decay, long-lived. Or picking another reaction, the lambda 0, a neutral lambda baryon, could decay to a proton. Good, another baryon, conserves baryon number. And a pi minus to conserve electric charge, and that was a slow decay. Or in the case of the kaons, which are mesons, they're not baryons, it could decay to a muon, an antimuon that is, a mu plus and a muon type neutrino. Or perhaps hadronically, a K plus can go to a pi plus pi 0, or even pi plus pi minus pi minus. Pi plus pi minus, I should say, to conserve electric charge. And those were examples of slow decays. So what's happening here? And well, before I get there, note that the sigma and lambdas are baryons, and baryon number is conserved in these production reactions as well as in these decays here on the left. So what was concluded was that these strange particles had a conserved quantum number called strangeness. And that quantum number strangeness is conserved when produced in strong or electromagnetic reactions or collisions in general. So you have to conserve strangeness in such reactions. But strangeness is apparently not conserved in the weak decays of these particles. All right. Now, let me give you a convention. We have to create a new quantum number that's conserved on both sides of the reaction, at least for the electromagnetic and strong nuclear force. So the charge kaon K plus and the neutral kaon K0 have a strangeness of +1, 1 unit of strangeness. All right. However, the sigma plus and lambda 0 baryons have strangeness -1. So they have the opposite strangeness, if you like. Antiparticles have opposite strangeness, which means the negative of the particle's strangeness. So namely, that means for the K minus, which is the antiparticle of the K plus, instead of strangeness +1, it's strangeness -1. Or for the K0, the antiparticle of that is actually an anti-K0, so K0 bar. So instead of strangeness +1, it's strangeness -1. And the antiparticle of the sigma plus would be the sigma minus. So instead of strangeness -1, it would be +1. So opposite strangeness. However, interestingly enough, some particles have even larger values of strangeness. The C minus has strangeness of equal to -2 units, 2 units of strangeness, -2 units for the C minus. And the omega minus has -3 units of strangeness. So stranger upon strange, right? But as I said, you have to balance strangeness on both sides of the reaction, at least for electromagnetic and strong force reactions, but not for the weak force. It violates strangeness conservation explicitly. And as we shall see, it violates flavor conservation, which means it changes the type of particle from one fundamental type to another. But in addition to strangeness, there is more. There's charm and beauty, and even a little truth. So it turns out, as accelerators reached even higher energies, additional particles were observed that also could be produced in strong or electromagnetic interactions, but also had only slow, weak decays. These included the D mesons, the neutral versions D0, the charged versions D plus and minus, and the B mesons, again, the neutral versions B0, charged versions B plus and minus. These are mesons, not baryons. But these are just a few of the examples. You could have excited states of them. Thus, for those particles, additional quantum numbers are required that are conserved in electromagnetic and strong interactions, like strangeness is conserved. And historically, for the D meson type particles, that new quantum number is called charm, or charmness. And for the B meson type particles, that is beauty. However, now we call that bottom. And eventually, experimentally, it was determined that these new properties, strangeness, charmness, beauty, all could be identified as properties of unique quarks that are actually constituent building blocks of these hadrons. That is, that these mesons and those baryons were not fundamental particles. They're made of other particles called quarks. So joining the up and down quark, which we're introduced to explain, for example, proton and neutron makeup and other particles, we have the strange quark, S, the charm quark, C, and the bottom quark, B. Now, how does truth come in? Well, in 1995, a sixth type called the top quark, originally called truth, hence the truth, joined this family as well upon its discovery. So, what do we have? So these last couple conservation laws, strangeness, charmness, beauty, are representative quarks, which are fundamental particles apparently that are building blocks of hadrons. So we can talk more about that in the so-called standard model picture of particle physics. So what are the standard model particles? And it turns out the quarks can be arranged into 3 generations, very much like the leptons. So at the bottom 2 rows are the leptons. We have the charged leptons, the electron, the muon, and the tau lepton. And we have the neutral variety, the neutrinos, which remember from the lepton number lecture or conservation law that we have an electron type neutrino, a muon type neutrino, and a tau type neutrino. In the quarks, we have something similar. We have the up and down quark, but we also have strange and charm in the middle column here, and also bottom and top, which used to be beauty and truth. All those particles are fundamental spin 1/2 particles. Their mass generally increases from one column to the next, that is, from one generation to the next. So the top and bottom quarks are much heavier than the up and down quarks. And in the case of quarks, they have fractional electric charge, right? The electron has charge, well, if it were an anti-electron plus E, but it's actually -1 unit for the electron and for the muon and tau lepton. The neutrinos are neutral, so they have 0 electric charge. The up quark has charge plus 2/3 of E, so it's 2/3 the charge of the proton. And the down type quark has charge minus 1/3. That is 1/3 of the charge of the electron. So, but all these quarks, down, strange, and bottom, all have charge -1/3 E, and the up, charm, and top quark all have charge plus 2/3 E. Very strange. They're fractionally electrically charged, at least compared to the electron and proton. And there are also antiparticles for each of those. So you would have an anti-up quark, an anti-down quark, an anti-strange quark, and so on. And the charges would then be the negative of the particle. charges. Okay, so that ends this lecture on the conservation laws. We'll follow this with a short one to go over some reactions and see which conservation laws are violated and which are not, with some examples.